Okay, we'll start with this sequential circuit design, a topic that we started last time. I'll take up another example today. Of course, want to emphasize the steps that we followed last time, somewhat similar steps. But finally, we will also look at what are the difficulties that come, especially when we are designing circuits which require more than one secondary variable. And we will see that as we see the design of this example. So the example I am taking today is, consider a circuit with one input x and one output z. The output should suppress every alternate pulse on the input starting with the first. The role of the output is that it should pass every alternate pulse and suppress every alternate pulse. So the first pulse should be suppressed on the input and all the other pulses should be passed. The input need not be periodic or anything. The width of these pulses also need not be, it doesn't really matter, because we are not here working with any clocks. So x is a input waveform. It is, you basically get a set of pulses here on x, and the z, the output, is also a waveform, similar waveform, except that irrespective of what the widths were, so this pulse got suppressed, this pulse got suppressed, whereas this got passed and this got passed. So I need to design a circuit for implementing this waveform. The starting point will be, of course, identifying all the total states of the system, very similar to all the stable states that we have, and exactly the same procedure as we followed last time. So once I have my waveform, I can identify, okay, this is one stable state. If the input continues to be 0, the output also would have been 0 and I would have continued in this stable state. This is another stable state. This particular stable state is input is 1 and output is 0. But also the fact that this particular input 1 corresponds to, we can call them to be odd and even pulses. So this input 1 corresponds to an odd pulse, and that is one stable state. Now we come to this is very important here. So this is, of course, input is 0, output is also actually 0, but this need to be distinguished from the previous state 1. The reason is because now the odd pulse has passed. So now what I am going to expect is, so this is what is capturing the history of the input in terms of, so that the input is 0, we still have to have a separate stable state 3, and I cannot map this onto 1. So I have another stable state 3. And now finally, when the input again goes 1, now this particular 1 corresponds to the even pulse which needs to be passed. So I have another stable state 4 for this. And once this pulse passes, I will go back to 1 and I will repeat this process over and over again. So I need 4 stable states over here, or 4 total states over here, and I have only one input and I have only one output. In this particular problem, it's not very important to talk of fundamental mode because there is only one input, so only one input can change at a time. So we don't have this. Except that still the fundamental mode property is important, that the input doesn't change too fast. If there are transients that are going to occur, the input should change only after the circuit reaches its equilibrium. The transients die down and the circuit reaches equilibrium. We will understand this once we look at the implementation. So I will draw a primitive flow table for this. The primitive flow table looks like this. So I have states 1, 2, 3, 4, and I have the states 1, 0. So I go to this. So I will go like this. When I go to stable state 2, when I go to stable state 3, I will go in this manner, and so on and so forth. This one is a very, very simple flow because there is only one input. So I will be going, and I will be following this path continuously. Okay, so there is, as far as the flow table is concerned, there is no complexity. Now there is a very important step over here, and we will follow one step of, basically now we have to, there is no reduction that's possible. We can't do any mergers because none of these rows are compatible. So, so that step is avoided here. But of course, if you have a more complex primitive flow table and reduction is possible, you should go through the reduction. because there is no reduction possible. So I have 4 states and I need to encode them. So now I have 4 secondary states also. So I need to encode them, and I need at least 2 variables, 2 secondary variables to encode them. Now how do I encode these using these 2 secondary variables? So I choose one encoding, and this particular state encoding follows a simple counter type of an encoding. Like what we do is we take the state 1 and say it is 0 0, state 2 we take it and say it is 0 1, state 3 is 1 0, state 4 is 1 1. That is of course because we put states 1 to 4, so that is why it is 0 0 0 1 1 0 1 1. It is a fairly straightforward encoding, and we will now, once I have done this encoding, I can reduce this, convert this table into a state table. But at this stage I should also assign the outputs, because I want to have something very, completely deterministic. I should assign an output for these cases. So I can assign, following the same logic, I can say that early change of the output. So which will mean that this will be 1 0, this will be 2 0, this will be 3 0, this is this will be the outputs that will correspond to early assignment of the output. So once I have done this, then I can draw my state table. So the state table is simply nothing but what we had in this particular, in this I just have to replace the states by the proper encoding of the states and write it as inputs and outputs. And the idea of writing this as inputs and outputs is to get the specification of the combinational logic block. Because after all, the model that we have over here is we have this combinational logic, the Z output, and of course now we have 2 inputs. And we have, so this corresponds to y1 and y2, this corresponds to the excitation y1, y2 and y1. So I need to arrive at a table, which is, I call it the state table. So that is the table that defines my combinational logic. It defines as a outputs as a function, the 3 outputs as a function of the 3 inputs. And I can draw that table, and this table is nothing but straight away the conversion of course not the primitive, I should say the reduced flow table. Of course here reduction is only, there is no reduction, there is only assignment of the outputs for the transient states. So now I have this. So this one is a direct combinational logic design problem. I can use my Carnot map method, or I can use any method to do the design. Let us see what the design is. If you consider the output is corresponds to rows 5 and 7. So y2 will be eliminated in my output. So output will be, if you consider this output will be y1 dot x, because this is one row 5 and 7. So y2 will get eliminated and I will get y1 dot x. If you consider y2, if you look at y2 and x are exactly identical. So y2 will be x. If I now consider y1 is a little more complex logic. y1 is 1 corresponds to, so it is sigma m 2 is this row, 4 5 7. This is the logic that is for y2. And in this case you can do a reduction, and you can see that 4 and 5 can combine, and 5 and 7 can combine. 2 will not combine with any of these. It is fairly easy to see, and so I can have the equation for 2. The term will be, 2 will give me y1 complement, y2 x complement. When I combine 4 and 5 will combine and I will get y1 y2 complement, and I will, when I combine 5 and 7, I will eliminate again y2, so that will be the same as here y1x. So now I have got this y1, y2 and z in terms of small y1, y2 and x. So this is completely defines my combination logic.
y1 is sum of min terms. So y1 is equal to sum of min terms.
Oh, sorry. Yes, it's y1, not y2. This is this particular column here. So now I have this expression for y1, expression for y2 and expression for z, and this is what I have again written down over here. Now I have to implement it, and I will implement it and check that what I intended actually happens or not. Remember, one decision we took in terms of the implementation was that we don't have to have any additional delays, but we can just use the delays that are provided by the components themselves. So that's fine. So I will take this equation and draw a circuit diagram for this. So let me draw a circuit diagram. So I have, let's say, I will still draw this box. These delay boxes of course are not really required, but let me just draw a box. And I have this. This is my x input, and this is my logic that I need to define. And if you look at it, so this is, let us say, my y1, so this is y1, this is y2, and this is z. So now let us look at what are the connections. So in terms of y2 is nothing but a straight this connection, because y2 was x. Z is nothing but, so this is y1 and this is y2. So z is nothing but y1x. So I can have now in this case, of course, there is y1 complement, y2x complement. So I will have one AND gate for this, 3 input AND gate, which is y1 complement, and I have y2, this was x complement. Another is y1, y2 complement. So I will have y1, y2 complement. And the third one, I can use the same output here that we had. And this is the one which is going as y1. And this circuit, we will spend some time and study this circuit very closely. I said I had this notional delay D, which I have made it 0 for a moment. I don't put any delays, I just try to use the gate delays. But now if I look at it, what happens in this circuit? What I need to do is, when the input is 0, 0, output has to be 0, and I am in an equilibrium state, and remember the equilibrium was defined as excitation being same as the secondary variables. So if I have 0, 0 as x is 0 and your y1, y2 are 0, 0. So when x is 0, your z of course output is 0, and this output is also 0. Here I am getting a y2, so this is 0. Here I am getting a y1, this is 0. All these three are 0. So this generates y1 to be 0. And when x is 0, y2 is of course 0. and I have no problem. I will continue to be in this stable state. But when x becomes 1, what happens? Remember that when x becomes 1, what should happen over here from this table? y1, y2 was 0, 0, and when x becomes 1, I should generate y1, 0, y2, 1, and z, 0. So now when x becomes 1, there is really no problem because x is anyway y2, so this is my y1, y2. So this was 0, 0. Now with this condition, when x becomes 1, y2 of course will become 1. Because y2 is nothing but x, and I will make a transition to 0, 1, and once this becomes 1, x is, as long as x remains 1, this 1 will remain here. I am just getting this 1 back, and I will remain in this state, and as far as the z is output is concerned, x is 1, but because my y1 is 0, and y1 will remain 0 because this term is 0. X is 1, so this term is 0. Y1 is 0, so this term is 0. All these three terms are 0, so I will just remain in 0, 1. So again there is no problem over here. That is, I make a transition to this and remain in this transition as long as, remain in this stable state as long as I am in 0, 1. Now the problem starts. The problem is like this. I am now going from, what do I need? So after this, what do I need? I have my y1, y2 to be 0, 1. And now when x goes to 0, what do I require my y1, y2 to be? I should actually make finally a transition to 1, 0. Output of course should remain 0. Now as soon as this x becomes 0, the problem that comes is when x becomes 0, if immediately my y2 also becomes 0, x is 0, one has to, of course output I have no problem, output will remain 0 because x is, goes from 1 to 0, so output will remain 0, y1 was 0. But now how can the y1 become 1? Because I need y1 to become 1. y1 can become 1, there is a path actually for y1 to become 1. If y2 was 1 before and you sense x to going to 0, so y2 1, x 0 and y1 0 will make this actually 1. If you look at this particular gate, x0, so if it gets this value x0, y2 1 and y1 0, sorry x0, y2 1 and y1 0, these three inputs, all of them will generate this to be 1, and this one will hold on. How will it hold on? Though of course after a time delay d, if I have a delay d, y2 of course will become 0 because x is being passed on as y2. So this one cannot remain any longer as 1, it has to go to 0. But because once this became 1, this one will, if it comes over here, this one this y1 1 and y2 0 will make this one, and this one will hold on. So this will eventually become 0 and this will hold on. But an important point over here is, this is the gate which generates this transition. Please remember, in synchronous sequential circuits, these things were being done by the clock. It was very nicely differentiating between the present state and the next state. Here there is no such clock. So I have a problem. As soon as I go x to x, as soon as I go zeros, if it immediately comes over here, then I have no condition here. I basically have 0, 0, 0, which will become 0 and it will never able to make it to, this will never become 1, and if this doesn't become 1, I will never go to, so I will essentially instead of going to 1, 0, I will end up going to 0 0. So obviously this circuit is not acceptable. Let me actually redraw the circuit because so let me just write the names of the symbols, not show the connections. So I have this X, this one is XY1, this is Y1, Y2 complement, this one is Y1 complement, Y2 X complement. And this is my Y1 and this is my Y2. So I have this. So now as far as now my problem is my Y1, Y2 is 0 0 and X has just become 1 to 0. Sorry, Y1, Y2 is 0 1 and I have become 1 to 0. So I should actually have gone to 1 0, but I end up going to 0 0. The reason this happens is X is just Y2, so and X makes a transition from 1 to 0, immediately it gets reflected in Y2 and there is no time left for. So this particular gate never becomes 1. If once it has become 1, it will be able to hold it through this particular gate, because that particular one. So I have a problem over here. So we say that okay, this problem perhaps comes because of the fact that I have this XY2, there is no delay. So what I can do is I can introduce some delay. I can put two inverters, I can put a buffer, I can put some circuitry inside, which functionally still Y2 is still same as X, but I introduced a delay over here. Now because of this delay, now what happens is this particular Y2 will still remain 1 when X has become 0. So Y1 was 0, so this will be 1, this input is 0, this input is 1 and this input is 0 temporarily till the time the Y2 actually becomes same as X, which will be after the delay which is given by this logic. So in this time this will become 1 and this 1 will come back through this and this 1 and eventually this becoming 0 will make this 1 and of course it will make this 0 and then I will end up having a proper output and I will remain stabilized. And this is a very important analysis that we need to do, and the problem that comes over here is not very difficult to trace why this problem has come. The problem has come because of the fact that I expected 0 1 to change to 1 0. The source of the problem is not just the fact that I don't have a delay over here. That's not really the problem. We can introduce the delay, but the problem is how do I introduce the delay to make sure that it actually will wait till that change occurs. I am not going to count the delays on each path or for each transition. I am not going to keep on computing my delays. So the source of the problem is I wanted a state change which involved not change of one variable but change of two variables. Each time you are going to make a state change which involves change of more than one secondary variable, you always run the risk of going through the 0 0 state. There will be any transitions which involve more than one secondary variable to change, implies that there will be momentarily there may be a situation where the secondary variables will be in, because after all you cannot balance all the paths for all the transitions, that's not possible. That delays are dependent on parameters which are not even under your control, the depth of the logic, what inputs are changing and so on and so forth, they will all determine the delay, so it's not possible. So whenever there is a state change which involves more than, so how do I avoid it? I can go back at least in this problem, my state changes are very, very simple. I am only going through a sequence of states and I am not going from each state, I go only to the next state. It's almost like a counter. So what, instead of the way the encoding I did was this, 1 0 0 0 1 1 0 1 1. I can do the encoding in this manner. Actually this problem will come, in this case this problem can also come when you are going from state 4 to 1, because you are going from 1 1 to 0 0. When you go from 1 1 to 0 0, you could be going through a transient of 0 1 or you could be going through a transient of 1 0. To ensure that we actually go from 1 1 to 0 0 would imply that both my secondary variables, the delays are exactly equal on both the paths and they change exactly at the same time, which is not possible to ensure all the time. So what happens is, I could have, in this particular case, I could have done something simpler. I could have encoded this as 0 0. I could have encoded it as 0 1. I could have encoded it as 1 1, and I could have encoded it as 1 0. Now what happens is, each time a change takes place, I go from 0 0 to 0 1, I go from 0 1 to 1 1, I go from 1 1 to 1 0, I go from 1 0 to 0 0. All my transitions now, which correspond to the equilibrium states, all of them correspond to only one change of secondary variable. And if you encode it in this manner, it is possible that we will avoid the type of problems we faced. But sometimes, so we will of course do a much more greater analysis of it. Let me just define the problem. We will take up more examples and also how to avoid it in the next class. But let me first define what the problems are. State assignment of secondary states could result in what are called races and cycles. We call races. So this is basically what happens is, when the term race essentially comes from the fact that there are more than one variable. So their delays, they are racing across the circuit, the delays are unequal, and finally when the outputs come, you are not sure which one will arrive first. So that's a race condition. So these races are critical and non-critical. Critical races are those which basically, see what is, when you are doing a state assignment, you are really not bothered about the implementation of the circuit. You do not know that you are going to use these gates, the gates that we use, like we are going to use AND gates, OR gates. What is the delay of these gates? What's the technology? What is the depth? You are not really considering at this time. So if the problem can be avoided in a technology independent way, in an implementation independent way, that is the best solution. Not considering the individual gate delays, but at the time of your state assignment itself, you can avoid the problems. So that's the solution that we considered before. You should actually do the design and make sure that the design works with the other state assignment that we considered. So what happens is, a critical race is a situation when you have assigned your states, when you can actually, irrespective of what the implementation is, you can actually find out that if the inputs change in a different manner, the secondary variables change in some manner, that is more than one secondary variable is changing, and they change in a manner so that they result in a wrong final state. The state that you reach is a wrong state, then it's called a critical race. So this particular situation was a critical race situation, because when I was in 0 1 and when x went from 1 to 0, instead of reaching 1 0, I reached a stable state of 0 0. And it's a stable state, it will just remain at 0 0. It is not that it's going to change unless the inputs change. So such a race is called a critical race because of the fact that 0 1 didn't become 1 0. It resulted in first becoming 0 0. That's because first the y2 changed instead of y1. If y1 has changed, first situation may have been different. So y2 changed first, and this is called a critical race, and critical race results in a wrong functioning of the circuit. It's not difficult to see when a critical race arises. We will discuss that in a moment, but let's first define also the non-critical race. Sometimes you may go through some transients, but finally reach the state that you actually wanted to reach. So then it becomes a non-critical race. So you can sometimes permit more than one secondary variables to change, but you can end up in a non-critical race. We will also see when a non-critical race results. Cycles, when you actually direct your transition through a set of secondary states, then it's called a cycle. You basically go from one stable state to another stable state, but you actually direct it through some transient states. This you can do it as part of your design itself. We will again consider this part also in detail. So that's called, defined as a cycle. Of course, cycle should terminate. Cycle should terminate in an equilibrium state. Otherwise, you will have a non-terminating cycle. You may be going, so it will essentially generate some type of an oscillation. It's continuously going from one state to another, returning back to another state, and so on and so forth. So then it will become a non-terminating cycle. So typically, cycles is a set of transient states through which you direct those transient states generate a cycle, but finally you should have a terminating cycle. So let's look at what are the conditions. If you just look at it from the point of view of your flow table, what are the conditions for, let us say this is my flow table, when will you have a non-critical race? If you consider a particular column in which there is only one stable state, let us say I am considering there are two inputs, and I have done my sum state encoding. This is a stable row. This corresponds to 0, 0, 0, 1, whatever, 1, 0, 1. If I am trying to make, so let us say my input changed from somewhere. It's changed from, let's say this is my input x1, x2. No. This is my. So if this particular input changed from this to this, wherever, so let's say I want to actually go from anywhere to anywhere. So I go, but I will finally be directed on to whichever state I reach, I finally will be directed on to my state, stable state 1, 1. I can make my secondary state assignments in some manner, so that for this particular input state, so then there will be a non-critical race that will result. I will make some transitions. We will of course consider a more detailed example of this when it will clear. So in this particular case, a critical race results because there are columns in which there are more than one stable state. In this column also and this column also. So when there is more than one stable state, and still if you want to make the races to be non-critical, that is, you should actually go to the final state, you have to bother about your state assignments. You have to do your state assignments in a manner so that you will. So now we will also see when we are trying to avoid this critical and races, then you will also see that how we will now play with the transient states. Previously till now we have assigned transient states completely on the basis of what the final state is going to be. Now we will see that sometimes we may have to assign transient states to take care of a particular direction, that is a particular set of transient states occur, so that finally I reach a stable state that I am looking for. So this is the point note that I will stop now. What we have over here is, so I will just indicate that what is the problem that we finally encountered in the design. We have this races and cycles, so we identified a problem in our design. The type of encoding we did resulted in a race condition, and it resulted in a critical race condition, and to avoid critical race condition, one way that we could solve is to encode it in a different manner, and this will be an assignment for you to take that encoding, design the circuit and make sure that races do not occur. We will stop here.